Today, I will talk about physics-informed learning. This is something I have started to study maybe 1.5 years ago. And today, I think I have studied it long enough to start talking about it with simple words. So this was, I have conducted this work within the division, the division of decision and control systems. And this is joint work with John New, Miguel Agar, and Karl-Henrik Johansson. So first, I will talk about some, I would say, vocabulary that I will use after, such that we will all talk the same way. So first, what is a machine learning problem? So machine learning problem, it's this kind of thing. So you have an optimization problem because you're trying to find the argument that is minimizing a cost function. And this cost function, compared to traditional optimization, is a sum over some loss that is defined depending on data. So this loss, this cost function, is data driven because mu e and yi are known. I mean, this yi are the measurements and mu I are the input parameters. And u here is the variable that is optimized on. So all along the talk, when a letter is in bold, that means that optimization is made over this letter, just to simplify the writing. So this is an optimization problem from a data-driven perspective. A differential equation is is as follows. So it's made of three things. It's made of an equation. So here v is a function, and we take its partial derivative along t, plus some operator n acting on the function v, and it's taken at t and x. And we want this to be equal to 0 for every t and x inside the domain. So t is usually the time, so it's belong 0 and capital T, and omega here is a domain. It's a spatial domain. And it can be like, usually it's a subset of Rn, a closed subset of Rn. And the other thing that we have is called a boundary condition. So it's the value of the function at the boundaries of omega. So let's say that omega is between 0 and 1. So this is the value of v at x equals 0 and at x equals 1. I will not talk about the relation between the partial differential equation itself and the boundary condition, but sometimes depending on the boundary condition, you might not get uniqueness of a solution, or you might even not get existence of a solution. And something that is always provided as well is an initial condition. So this is the value of v at time t equal to 0. And this is given as a function. So once we know that, then we can solve and try to find the function v using, for example, numerical schemes if it's too difficult to solve, or if it's quite easy to solve, then you can try to get an analytical solution. Let me just briefly come back on the operator n. So this operator can be, for instance, a partial derivative of v along x. This is something possible, for instance. Okay, so the funny thing comes now. Actually, there are many examples that can be modeled using machine learning and or differential equation. For example, weather forecast. There exists some methods that are using machine learning and knowing the weather at some given position, knowing the temperature, for instance, then you can predict the temperature around, and sometimes you can even predict the future. So this is called time series prediction. Knowing past values, then you can predict future values. But you can also use a model for that. And then you will use a differential equation with, for instance, Navier-Stokes equation, and you will try to predict the near future by solving the equation numerically. And then you will get the temperature tomorrow, for instance. And this is the case for many other examples, like traffic jam, stock price, a trajectory of a robot. There are many, many things that can be modeled using both machine learning or differential equation. So this is the funny thing. Then two questions arise. can we use machine learning to solve differential equation? And can we use differential equation to solve machine learning? And here in this talk, I will just talk about one direction. So how to solve differential equation using machine learning. So first, who was the first one who decided to study this? So it was in 1990, so not that long ago, like 30 years ago. And this paper, so by Euclid and Seo Kang, maybe my pronunciation is not very good, proposed some neural algorithm for solving differential equation. And then 8 years after, so quite a long time ago, a long time after, some Lagares proposed to use artificial neural networks to solve differential equation, and then like 2 years later proposed a similar methodology but with a very irregular boundary condition. And then after we have to wait for 13 years for Kate Rudd to propose to write his PhD thesis actually on the topic. And then he kind of formulated the problem and showed what has been done before. And the real breakthrough was in 2018 with the DGM algorithm, which was a discretization of some Galerkin method using neural network. They proposed very theoretical results that were quite interesting and novel. And maybe the most important paper is the one in 2019 about who proposed really a framework, and then you just have to fill in the gap to solve your problem using machine learning. So this paper is maybe the basis of what I will explain today. Note that this is a very recent paper. So this research area is very new and it's still open to many things. And I will, at the end, talk about some challenges that we're facing today. So since I don't know from which background you are and I would like to talk to everyone, I would just briefly introduce what is a neural network. So a neural network unit or a single layer neural network is a function h, which has two parameters, w and b. W is a matrix and b is a vector, and nu is the input. And then it's equal to phi, so this is a function phi called the activation function, which parameter, so it's element-wise activation function, and the parameters are, its parameter is w times v, times nu, plus b. And W is a matrix with capital NN line. That means that it has NN neurons inside. And this is the bias. And if we want to talk about deep learning, then we will introduce several layers. So multi-layer neural network, which is a composition of the H function many times. And so here, the function is u theta. Theta is a tensor of parameters, and nu, so it's input. And then you do first one layer, then two layers, and up to L-1 layer. And then since you want a linear output, because we want a function that does not saturate, for instance, then we multiply it by W and plus B. So this is the function, the neural network that we will consider in the sequel. This is called as well multi-layer perceptron. And there is something very interesting derived by Ornick, and it's the universal approximation theorem. It states that a neural network can approximate any smooth function arbitrarily close, provided a sufficient number of neurons. So if you want to approximate the solution of the PDE, for instance, then if the solution is smooth, then you can consider a neural network with many neurons, and you should be able to approximate your solution very well. So now let's move on to some example and why are we doing this. So I am working specifically on traffic density estimation. So this example is, of course, based on that. So this is a spatiotemporal diagram. So I don't want to explain you what it is, but just say that it's a figure that you want to reproduce. You want to estimate it because you know the values of each pixel only on the black lines. So you see there are 4 black lines, and you can measure the density at every point on these black lines. So you don't know many things, and you would like to know the density everywhere, knowing only these black points. So what you can do is use deep learning, so machine learning, and then this is the output. So as you can see, it's not very good, a very good estimation. I mean, it's very good on the trajectories, but since the trajectories are quite far, the machine learning algorithm does not know how to fill it. And then he fills it with something that is not physical, just something. And if we're using a PD, so this is the model that we're using, knowing the values on the black lines, then we get this. So you can see it's very close to the original one. There are some discrepancies at the beginning here, but it's mostly the same. After a while, at least it's the same. And you can prove that it's the same actually. So here at this point, many people will say, but why are you doing then machine learning? Because apparently it's working very well using the partial differential equation. The reason for that is because this figure comes from a simulation. I mean, we just simulated it, and then we assume that we knew only the measurements on the black lines, and then we are trying to reconstruct the density in between. But if you're taking some real data, so this is real density on the road, and then you can measure on the black lines. Then if you use a model, you will get this. So this is a very bad estimation, but the reason why is because the model is not very accurate. I mean, this is not the real situation on the road. So you have a very bad reconstruction. But if you are, then you're thinking maybe we should use something different. And here is a summary of what I've said. So if you use a data-driven framework, so if you use a machine learning, for instance, then you get a good estimation. You get a good estimation of your function if the data set is quite large. You're most often robust to noise and disturbances. You do not have the curse of dimensionality. So this means that if your V function is multidimensional, let's say belongs to R 1000, then you can still solve it. And sometimes you can infer some idempotent. So for instance, you can maybe infer a model to your system. But it requires a very large computational time. There is no convergence proof. That means that you're not sure that at the end you will get the result that you want. You will get something, of course, but maybe that's not what you want. And so it requires a large data set. Now, if you're using a model base, so if you're using partial differential equation, for instance, you do not need many measurements. You just need boundary conditions and initial condition. It's very fast to compute. You can use, for instance, numerical scheme like Godunov scheme, and you can get a solution relatively easily. And you can even get error bounds on the solution because, I mean, for hundreds of years, people have studied algorithm to compute solutions. So now it's very well documented, and there are many things that you can do. And one, for instance, is to know how good is your simulation compared to your original model. And the problem is that sometimes it's not very robust to noise. That means that if you have a noisy boundary conditions, then you might get something really different. And it requires a precise model. That means that you need to know the model perfectly. Otherwise, you will not get the solution that you want. And it's subject to curse of dimensionality. Indeed, if you have the V function on the PDE that is large, that is of large dimension, then you will never be able to compute something. You will need to use some other techniques like time source decomposition, this kind of thing to get a result. So now the idea is to get the positive points of both. So can we use data-driven and model-based simulation tools? And there comes what's called a physics-informed neural network. Maybe it's not too late to say that, but if you want, you can interrupt me and ask me questions if it's not clear, of course. And at the end, you can talk with me. So here is a machine learning problem. Here is a differential equation problem. And from the machine learning problem, we will take the optimization problem. Then we're trying to solve an optimization problem over a cost function that is written this way. And from the partial differential equation, we will take the boundary condition, and they will become the loss function here. So what we want to do is to find a function u of theta parameterized by theta. So theta is a vector, is a tensor of parameters, such that the measurement error is very small. So you want to minimize this. This is a mean square error of the difference between u theta minus yi. So this is a measurement, and this is where you have done the measurements. This is equal to nu I here. And you have some constraints. So it's you want to solve this optimization problem such that the partial differential equation itself holds. So you want to solve this for any t and x belonging to 0t times omega. And instead of a function v, here you have your function u theta. Okay, is that clear? So this is a learning under constraint problem, and it's not very easy to solve. What we can do to optimize over PIN, so PIN is physics-informed neural networks. This problem is called physics-informed neural network problem. Now, me, sometimes I call this physics-informed learning as well. So you want to find the optimal parameter theta such that you have minimized your mean square error between your value and your function and your measurements, such that the partial differential equation holds. Just briefly, I can talk about this equation. So it seems weird to differentiate a neural network depending on time and maybe on space as well. But actually, since this is a neural network with smooth activation function, then u theta is smooth. So then actually you can derive it, and you can derive it quite efficiently using automatic differentiation. So this is something that has been well studied. And now today you can get the value of this function for any t and x. And now what we will do first is, since this is an infinite dimensional constraint, that means that it should hold for any tx belonging to a domain. What we will do is instead consider integral. So we want this to be equal to 0. That can be seen similar to a norm. We want the L2 norm of this to be equal to 0. And then we will apply something that is classic in constraint optimization. We will use a Lagrange multiplier, lambda, and we will write the optimization problem this way. So let me explain what happened. So this is a constraint, and that's moved into the cost, ponderated by some coefficient, lambda, that is positive. Then if we minimize everything with lambda strictly positive, then it's the same than solving this problem. Okay. And actually, it has been proved in some paper that provided lambda is strictly positive and an infinite number of neurons, then the optimal value of this taken at theta star is equal to 0. So it means the minimum of this is 0. So that's perfect. That means that we have solved this almost everywhere, and we fit the measurements. But the problem with that is we cannot solve this double integral because we cannot compute it actually, because it requires an infinite sum. So what we will do instead is to use a Monte Carlo approach, and we will discretize these double integral terms into this. So then we have samples ty, p, x, y, p. They are inside the domain 0t times omega. And we take many of them. We imagine that they are identically distributed along the domain, and we take the average. Then, once we have done that, if n phi tends to infinity, we recover our integral. And we can truncate it with n phi being large enough, and then we will get a very good approximation of our initial problem. So this formulation is actually the formulation that was written in the main paper of Récy and al. We can solve this problem using a primordial optimization. So actually, we want to solve this problem with maximizing lambda. This is something that is doable. Then we can talk a bit about the physics point n phi. So adding this cost, like here, means in a way that we have increased the total sum. And now the new total number of points is n plus n phi. So it's like enlarging the data set. Why do I precise that? Because we have seen earlier that for a data-based, data-driven method, the number of points in the data set is highly important. And the more points you have, the more precise your solution will be. And here, adding this term here is like increasing the data set with kind of, how can I say that? They are not, they are physics points. I mean, they do not exist. You do not know the value of u theta at this point, but they are, so it's fixtures term. So you can add them to the data set because you assume you know a model. Then you can also rate the confidence that you have in your model. Because if n phi is large, that means that you want your model to apply everywhere. And then you have a high confidence in your model. But if you are not that confident in your model, maybe because it's not perfect, then you can have a very small number of points. And then you will apply your model only times 2 times. And you will leave the machine learning algorithm find the value elsewhere. Then you can be not that confident in your model. Something else that is interesting is that you can say that the operator n is actually not well defined. Maybe there are some uncertain parameters inside. So you know how the model should behave, but maybe you do not know it that well. And that means that you have some extra parameters in it. And you want to solve now the optimization, minimizing this sum, but with mu being a parameter. And then you will try to find the best operator n. And this is identification. It's called identification in my field. That means that you're trying to find a model from measurements. And what you can do more is even you can, once you have estimated your n function, you can even use it in reconstruction. And this is done at the same time. So now let's come back to this example. So you know it's a real density on a road. So if you were using a model, then you got this kind of weird diagram. But this is because you assume your model was well known and it was this. So this part actually is not very well known. You know that it will have the form, the partial derivative of u along t plus something that is depending on u times partial derivative on u with respect to x is equal to 0. So you know these two terms perfectly, but you're not sure of this one. Then you can say, okay, if I am not sure, I will replace it by a sum from k equal to 0 to nk of mu k uk. So you kind of do an interpolation. You don't know what is a function, but you know it depends on u, and you know it should follow this. And then you solve your optimization problem, and you get this estimated density. So you see it's a lot closer to the real one. It's acceptable. It's something that we can use maybe in practice. So now let's make a summary of what I've said. So if you're using physics in for neural networks, you can get a good estimation with a small or large dataset. You're robust to noise and disturbances. No cross of dimensionality because you're using a machine learning. Then you can infer hidden pattern because you're using machine learning. And you can even do some model tuning. You can find the perfect parameters. But it requires a large amount of time And there is no convergence proof so far. So you're not sure that the output of your optimization is really the solution. Maybe the algorithm did not provide the real optimal solution. And even you're not sure that the optimal solution is the solution to your partial differential equation. It depends. So here are some challenges. So first, we would like to improve the convergence. What does that mean? We want less stochastic output. That means that if you're doing the training, if you're solving the optimization problem several times, then you should get something that is all the time similar. And today, this is not true. Sometimes you get something very similar, but sometimes not. You want it to be faster as well. So the fastest convergence possible. And you want, if possible, to get some conditions for convergence. I mean, under which condition and the operator n would you get the solution to your partial differential equation? And you would like to prove the approximation capacity for a broader class of operator n, because so far you can only deal with a very specific operator n. And I've not talked about it because we have considered only a single model, a single PDE. But if you have several PDEs that are interacting between each other, how do you solve this? Is this working? Actually, it's not working that well. It's like solving an optimization problem, but with multiple costs, and it's not an easy problem. Some general perspective. So you can investigate other neural network architectures. So as I said at the beginning, we have a very simple architecture. I mean, it's a multi-layer neural network with the same number of neurons in each layers. So maybe you can use something called long short-term memory that has proven to be very efficient. Maybe some convolutional network that are very efficient for image reconstruction. Or you can also change maybe the training procedure. Using a primordial update, using maybe some different algorithm. You can use also confidence intervals and try to compute confidence intervals over several optimizations so that you get bounds on your solution. And me, since I'm coming from control, I would like to extend it to some more control problem. So maybe that will not talk to everyone, but we would like not to estimate the past values of the density, but to predict the future, maybe the near future. So then we will need real-time observation. And how can we do that? And I would like also to use reinforcement learning, because then that means you can change the future. And in which way will you change the future? And some other broader perspectives, and maybe it's where you can come from, you come in place, is that I would like to use the PIN methodology in other domains, maybe in fluid mechanics, in signal processing, in astrology. I have seen some works, for instance, you're trying to estimate the blood pressure in your brain using physics-informed neural network, but maybe there are other things that are interesting to study. And I hope if we discover new context, maybe we will also need to add new things to the framework and try to see how that behaves in different contexts. So that might lead to some very interesting challenges, but I don't know them so far. In the talk, I have not shown many references, so here are some, and if you want, you can look to references inside these papers as well. So thanks for listening.